This should be a pretty short video about interpolation and Simulink. So kind of the goal is to show you how to do, I'm just going to show you 1D interpolation. And it actually ends up being a similar method that we used when we were doing interpolation at the beginning of numerical methods. And so I'm just going to do this with an example. It's a fairly similar example to what we've done before. I can't remember if it's exactly the same as an example we did for interpolation, but it's very similar. So I've got a tank with a bottom area of 100 feet, and it's used to store water. And the flow into the tank is given in the table below. So you have a flow rate in that's varying with respect to time. So you assume that t is equal to minutes. So for every 60 seconds is kind of in this table here, and then the flow rate varies. And so you assume that the flow rate is in feet cubed per minute. And so what you want to do is you want to plot the water height for that time. And so there's a couple tricks you need to do. Is if the flow rate is in feet cubed per minute, you're going to need to do some quick conversions depending on how you want to do this. And so actually, I'm just going to keep showing you. I'm going to show you all of it, all the slides, explain them to you, and go and actually do the example. And so the way I'm going to do this, I'm going to go into a lookup table block. And so what this will do is it works in the same way as the interp1 function does, except you need to kind of be aware of how everything works. So in this case, I have an x value and a y value. My x value is time, my flow rate is my y value if you're using interp1. And so in much the same way, it's kind of organized in the 1D lookup table dialog. The difference is that breakpoints is the x vectors, and then the table data is the table that you look up, that you interpolate. And so in this case, I need to put time as the breakpoints vector, and then I'm going to output a flow rate, in this case in meters cubed per second. And so then I'm going to input the time into that lookup table block. I'll show you. And the output is going to be in meters cubed per second. And then, so basically, what I'll do is I'm going to do a conversion. So I know how much, I know the flow rate in volumetric flow rate, and then I'll know it in feet cubed per minute. I change that to feet cubed per second by changing this table data here. And then I will divide by the area, 100 feet squared, in order to get the vertical change in the tank. And so I'm assuming that this is a rectangular prism of a sort, right? I'm assuming that the base, well, actually it doesn't really matter, because even if it's a circular prism, it's a circular prism, it's whatever, like a cylinder or any sort of polygonal prism. If I know the area of that, then I know that the volume is equal to area times height in a prism, right? And so I can divide by area and get the change in height. And then I'm just going to integrate that. I'm going to integrate that change in height. That's the rate of change of height, right? It's the flow rate. It's how the the height is changing in meters per second in this case, right? Or feet per second. Sorry, I think I messed up that calculation. Because if I divide by feet squared, I get feet per minute, and then I convert that to seconds and integrate it, and then that is the height of the tank at any given point. So I'm going to use this. I'm going to implement it in a 1D lookup table, and then I'm going to do some unit conversions, integrate it in order to get the change in height, or it's not even the change in height, it's just how the height of the water is changing with respect to time. So let's go ahead and do that. And so I've got a new Simulink diagram here. And so I'm going to keep this up to the left because I want to use this in my calculations and things. So I need to use this data somehow, so I need to interpolate it. So let's go in here. Let me show you where the 1D lookup table is. And it is in the lookup table library. If I click on that and grab the 1D lookup table, I can drag it over here. And so now I need to input my data, and this is where it gets different. So I need to double-click this, dialog comes up, and I need to input my data here. And so in this case, my table data is the flow rate data. And so let me do that right now. 0, 1, 2. Oh, the table data is the flow rate data. I already messed that up. 80, 130, 150, 150, 160, 165, 170, 160, 140, 120. And then this is just going to be 0, 10. And so again, breakpoints are the X values. The table data is the Y values. And so then I'm going to want to probably, I could go into my algorithm, and this is where I can change what my algorithm is. So I can change my my interpolation method to cubic spline if I wanted. I'm going to keep it as linear. And then I could extrapolate as well. I could say, all right, I'm just going to use a linear extrapolation and just keep it there. And so I'm just going to keep all of this as the standard default. And so now I need to, I know what the flow rate with respect to time is, so I'm going to need to use my time vector somewhere. And so my input, my X data is in minutes. So let me grab the clock, which remember that the clock is the time vector. It outputs the time as you go. And so what my goal is going to be is as this time simulates from 0 to 10 minutes, so I'm going to have to change my end time here, it will read in from this table what your flow rate is at that given time. So I need to have my units be the same. My time in my table is in minutes. I'm going to grab a gain block and convert to minutes. So this is T, and this is going to be T in minutes. And so I'm going to divide by 60. So I'm going to multiply by 1 over 60. And so what that does is that will divide the incoming signal time, which is in seconds, by 60, which gives me the current time in minutes. And now, in order to get the end time in minutes, 10 minutes times 60 seconds, right? I could type this in right here, 10 times 60, or I could just do 600. It's an easy enough calculation. And so now my output is in feet cubed per minute. And that's my flow rate, right? So I'm gonna do a slightly different solution than the one on the next couple slides. Is I'm just gonna keep the table data exactly the way it is, and I'm just gonna label my units as I go. This is actually a really good practice in both Simulink and MATLAB as you start to be solving real problems. You want to try to label what the units are too, so that if you come back to it, or if you just use it in general and want to understand what the units are, and maybe do some unit conversions as you're going, you can do that. So now what I want to do is I want to change it to feet cubed per second, because when I integrate it, I'm going to need to convert that. So in order to convert to feet cubed per minute, I'm going to need to multiply by 1 over 60. I'm pretty sure. Let me do that in my head. So yeah, if I do 1 minute over 60, so I need to multiply by 1 over 60, and this is going to be feet cubed per second. And now I need to convert, because I'm looking for the change in height over time. And so now I'm in feet cubed per second. I need to divide by the area, because I have the volumetric change per second, the volumetric rate, so how much it's filling. If I divide that by that area, it'll tell me how much the height is changing. And so I'm going to divide by the area. So I'm going to multiply by the area, which is 100. And so here I'm going to change this up a little bit. I'm going to say this is now going to be in feet per second. So it's going to be h dot, and that is going to be in feet per second. So that's me. I'm labeling the line. It's the change in height with respect to time, and it is given in units of feet per second. The reason I had to do these conversions is now I can use my integrator block. I don't think I need this anymore. I can use my integrator block in order to, I know that I have the h dot, the change in height with respect to time. I can use the integrator block to integrate that to just what the height is. So this will give me what my height is with respect to time. And because my h dots are always positive, it should the height of the water in the tank should always be increasing, or the volume should always be increasing, right? Because you have like some tank, you don't have an exit flow rate, you just have something entering it. And so what that ends up being is that the tank is just going to keep on getting more full, right? And so the height of the water is going to continue to raise throughout time. So let me grab the integrator block. I think my initial condition, so I was wrong, I still do need this. My initial condition is going to be, no, I must have accidentally clicked SolidWorks. My initial condition is going to be, I think I'm going to assume that it starts off with no water in it. So I'm going to set my initial condition to be 0. And now my output is H, the height of the water in the tank, in feet. Because if when I integrate something, with respect to time, I remove one of these, the rate term, right? And so I remove the over S, and so it's just feet. And now I'm going to plot it with a scope. And so I'm going from 0 to 10 minutes or 600 seconds, and let's run it. And that is the height of the tank, the height of the water in the tank with respect to time. So you can see it starts off at 0 and it slowly increases, and it looks like it's kind of reaching a plateau because my rate is now decreasing slowly. So the rate increases, and so it ends up being concave up at the beginning, and then the rate begins to decrease, which means it's concave down, which effectively means that it might end up approaching some maximum at some point. And so there is my answer. And so that's in a very quick example how you would do interpolation in Simulink. You just use the 1D lookup table, and if you have 2D interpolation, which I didn't even go over in MATLAB, you use the 2D lookup table. You can even have an n degree lookup table, and so you can add as many breakpoints as you need to in order to, and as many x, y, z, on and on and on vectors with a huge n-dimensional table of numbers, and then you can use that as you wish. This is something I use in my work a lot. I thought it was important to show you, and so that's that example. So what I want you to do is your first in-class problem is going to be use this, what I just showed you, and this is a previous example we did exactly. You have a table of temperature with respect to time, and I want you to predict the temperatures at times 9 and 5. And so it's a really simple example that I just want you to do in order to practice again how to use this lookup table.